Welcome again in the lecture number 4 of Engineering Mathematics 1 MTL 1025. In this lecture, we will going to discuss about the homogeneous function, Euler's theorem on homogeneous function and related examples. Right? First, we will see what is the definition of homogeneous function and their examples. Homogeneous function. A function of fxy is said to be homogeneous function of order n. A function fxy is said to be homogeneous function of order n or degree n if the degree of each of its term in x and y both is equal to n. Then this type of function is known as homogeneous function. For example, consider equation 1 is a polynomial of nth degree in two variable a naught xn a1 x to the power n minus 1 y plus a2 x to the power n minus 2 y2 dot so on an minus 1 x yn minus 1 plus an yn, right? Let us suppose this is equation number 1. This is homogeneous function of order n or degree n. How we verify? Take x to the power n is out of this term from equation 1. Then equation 1 can be written as a naught a1 y by x a2 y by x square dot so on an minus 1 y by x whole to the power n minus 1 plus an y by x whole to the power n, right? This term of bracket, see, this is something like a function of y by x, right? Then equation 2 is something like this, xn function of y by x, right? The equation 1 can be written in this form. Then this n represents the order or degree of function fxy, right? If any function can be expressed in this form, that is x to the power n function, this is phi or capital F, whatever you want to write. Any function can be written as, then this fxy is known as homogeneous function of degree n, right? Let us see some example of homogeneous. Consider this function fxy is equal to square root of x plus square root of y divided by x square plus y square, right? Take common square root of x, then this is 1 and second term becomes square root of y by x square 1 plus y by x whole square, right? And this can be written as x to the power 1 by 2 minus 2 and see this term. This term is something function of y by x, right? Then fxy is equal to f of xy equal to x to the power phi of y by x. Then this fxy is homogeneous function of degree minus 3 by 2, right? Consider second example. If we take second example, then suppose f x y is equal to this. F of x y, sorry, this color is not good. Let us consider f x y is equal to this, then x to the power 4 and from denominator x, then this equation is converted into this form. Then this fxy is homogeneous function of degree 3. Similarly, if we consider u is equal to, see this, u is equal to sine inverse square root of x plus square root of y divided by xy. See, this u we cannot express this as x to the power n into function of y by x, right? This u cannot be expressed, but sine u is equal to square root of x plus square root of y divided by x plus y. This can be written as x to the power minus 1 by 2 function of y by x. This sine u can be expressed in this form, but u cannot be expressed in this form, right? U cannot be expressed in this form. U cannot be written this. Therefore, u is not homogeneous. This u is not homogeneous function. But sine u is homogeneous function of degree minus 1 by 2. Right? Now, we already studied about the partial derivatives. What are the partial derivative? What is the meaning of the partial derivative? Now we will discuss Euler's theorem on homogeneous function. Right? Euler's theorem will help us to find the derivative or terms like x del u by del x, y del u by del y. For suppose given function, any given function, we have to evaluate x del u by del x, y del u by del y. Suppose you have any complicated function, then for that complex function, you have to evaluate del u by del x. That is not an easy task. And again evaluate del u by del y, then multiplied by del u by del x by x, and in del u by del y by y, and add them and solve them, right? Euler's theorem helped that if u is any complex function, but condition is that u is homogeneous. One condition, remember that Euler's theorem only you can apply if the function is homogeneous, otherwise you can't go for the Euler's theorem. If u is homogeneous function of degree n, then x into del u by del x, y into del u by del y is equal to n into u. Right? This is the result of Euler's theorem. But remember that this Euler's theorem is only applicable for the homogeneous function. First you check whether the function is homogeneous or not. If function is homogeneous, and in problem you have to evaluate x del u by del x, y del u by del y, that is nothing else but n into, that is order of the homogeneous function, multiplied by the homogeneous function u. Right? This is the result. Right? One thing is you have to remember, function must be homogeneous. Right? Let us see the proof of Euler's theorem. If u is homogeneous function of order n, then by definition of homogeneous function, we already studied that u can be written as x to the power n into function of y by x, by definition of homogeneous function. Since in the statement it is given that u is homogeneous function, right? If u is homogeneous, then u can be written as x to the power n into function of y by x. Right? What we have to evaluate? We have to evaluate x into del u by del x plus y into del u by del y. Right? Then consider this is equation number 1. Differentiating equation 1 partially with respect to x, del u by del x is equal to n into x to the power n minus 1 f of y by x, means first function derivative of second function, right? First function is f of y by x and x to the power n is the second function. Then first function f of y by x and derivative of x to the power n is n into x to the power n minus 1 plus second function x to the power n, derivative of f of y by x. What is derivative of function of y by x? First derivative of the function is f dash y by x, and again derivative of y by x, partial derivative of y by x with respect to x, that is minus y by x square, right? Now you have to multiply x by del u by del x. In del u by del x multiplied by x, then x into del u by del x is equal to this term, right? Just simply multiply that, n into x to the power n multiplied by x, then n xn f of y by x minus, this one is minus x square x to the power n, then x to the power n minus 2 multiplied by x, that is x to the power n minus 1 into y f dash y by x. This is equation number 2. Now again differentiating equation 1 with respect to y, right? If we are going to differentiate x to the power n function of y by x with respect to y, this term is constant, right? This term is constant term. Now differentiate this term f of y by x, then x to the power n is constant, derivative of f of y by x is f dash y by x, and derivative of y by x with partial derivative with respect to y is 1 by x, right? Then this term is x to the power n f dash y by x. This is nothing but partial derivative of u with respect to y. Now what we have to do? Multiply del u by del y with y. Now y into y, right? This is del u by del y, and now equation second gives us del u by del x. Now add these two terms, adding equation 2 and 3. Adding equation 2 and 3, left hand side becomes x del u by del x, y del u by del y, right? And second term of equation 2 and right hand side term of equation 3 is cancelled out. Then what remains at right hand side? N into x to the power n function of y by x, that is n into, what is this? This is nothing but u, right? Our homogeneous function. Then n into u. Then this is the complete proof of Euler's theorem, right? It is possible only when u is homogeneous function. Now we will solve some example, right? See one result of based on the Euler's theorem on homogeneous function. If u is homogeneous function, then one natural question arises that whether this Euler's theorem can be applicable only for the two variables? No, it can be applicable for the n number of variables also. If u is homogeneous function of three variables, say x, y, z of order n, then Euler's theorem is applicable. X del u by del x, right? X del u by del x plus y del u by del y plus z del u by del z is equal to n into u. Suppose if any other variable, four variables, fourth variable is w, del u by del w is equal to n into u, right? Means This Euler's theorem on homogeneous function is true not only for 2 variable or 3 variable, but it is true for n number of variables, right? Now see one deduction, right? One more result using homogeneous function. We already studied one example. U is equal to sine inverse square root of x plus square root of y divided by x plus y. We have already seen that this u is not homogeneous, but if we write this as sine u is equal to square root of x plus square root of y divided by x plus y, this sine u is homogeneous. This is homogeneous function of degree minus 1 by 2, right? This is homogeneous function of degree minus 1 by 2. Now, what this deduction states that if any function is not homogeneous in terms of x and y and its modified form, that is something like this sine u, is homogeneous, then this Euler's theorem is applicable for sine u, right? Not on u, but applicable on sine u, right? See the deduction. What is deduction? If z is homogeneous function of xy of order, and what is z? Z is f of u. Then x del u by del x, y del u by del y is equal to n f of u divided by derivative of f with respect to u, right? See the proof. Right? See the proof. Wait 1 minute. Here z is homogeneous function of xy. If z is homogeneous function of xy, then this z can be written as x to the power n function of y by x. Then we can apply Euler's theorem on this. By Euler's theorem, this can be written as x del z by del x. See, z is homogeneous function. Remember that z is homogeneous function of degree. Del z by del x, y del z by del y is equal to n into z. Now, it is given that z equal to what? Function of u. If z is equal to function of u, then what is del z by del x? Del z by del x is equal to del y del x of f of u, right? What is z? Z is f of u. This is equal to, what is derivative of f? Derivative of f is f dash u. And what is derivative of u? Del u by del x, right? Then this del z by del x, is equal to this. Now, similarly, del z by del y is equal to f dash u del u by del y, right? This del z by del y is equal to this thing. Now putting the value of del z by del x and del z by del y in equation number 1 means this equation here. Now from here we obtain x del z by del x means f dash u del u by del x plus y del z by del y, that is f dash u del u by del y is equal to n into z, n into z. What is z? F of u, right? See, f dash u, take it this side, then this comes f dash u, right? This is the proof of this deduction, right? Now see another remark. If V is homogeneous, if B is function of U and B is homogeneous function of x, y, z, right? Above deduction is in 2 variable, now this is in 3 variable. If V is function of U and B is homogeneous function of x, y, and z, then same deduction we can apply here. Del u by del x, y del u by del y, z del u by del z is equal to n into f of u divided by f dash u, right? Means earlier result is also true for 3 or more than 3 variables, right? Now we will discuss one more result. If z is homogeneous function of order n, then we have to prove this, right? We have to prove first, second, and adding first and second we obtain third. Means the important thing is we have to prove first, second, then adding these two we obtain this result, right? Let us start. What is given? It is given that z is homogeneous function of xy. Apply Euler's result. What is z? Z is equal to x to the power n phi of y by x or f of y by x. Then Euler's theorem says that x del u by del x, x del z by del x, since z is homogeneous function, y del z by del y is equal to n into z, right? N into z. C1, right? C1. This is after applying Euler's theorem on z. Now, differentiating 1 partially with respect to x and y, we obtained result 1 and 2, right? Now, differentiating this equation 1. Differentiating 1, del z by del x, partial derivative of x is 1 plus x into partial derivative of del z by del x is del 2z upon del x2 plus partial derivative of del z by del y is y del 2z upon del x del y, right? And partial derivative of y with respect to x is 0, right? This is left hand side, and right hand side is n into partial derivative of z with respect to x is del z by del x, right? Now take this term right hand side, we obtain x del 2z by del x2 plus y del 2z by del x del y is equal to n minus 1 del z by del x. This is first proof. Similarly, y del 2z by del y2 plus x into del 2z upon del x del y is equal to n minus 1 del z by del y. This is equation number 2, right? Adding equation 1 and 2, we obtain result 3. Now we will solve some problems related to Euler's theorem on homogeneous function. Now consider first problem. First problem is if u is this. Note that this u is not homogeneous. What is u? U is equal to log of x to the power 4 plus y to the power 4 divided by x plus y, right? This u is not homogeneous, but take exponential both sides. E to the power u is equal to x to the power 4 plus y to the power 4 divided by x plus y, right? This e to the power u is homogeneous function. Homogeneous function of degree 3, right? Then apply Euler's theorem. Sorry, deduction of the Euler's theorem. That is x del u by del x plus y del u by del y is equal to 3 into f of u divided by f dash u, right? This is equal to 3. What is f of u? E to the power u. What is derivative of e to the power u? E to the power u. This is equal to 3. Consider second example. If fxy is equal to 1 by x square plus 1 upon xy plus log of x minus log y divided by x square plus y square, then we have to prove this. We have to prove this. See whether this fxy is homogeneous function, right? If it is not homogeneous function, then we cannot apply Euler's theorem, right? Then what we have to do? We have to convert fxy as a homogeneous function and check whether it is homogeneous or not, right? Then this fxy can be written as f of xy is equal to 1 upon x square y by x to the power 0, right? Plus 1 upon x square 1 upon y by x, right? Second term, this can be written as this form. Log x minus log y, then this can be written as log of y by x, numerator, and denominator take x square common, x square 1 plus y by x whole square, right? That is, this is equal to 1 upon x square is common in all term, y upon x to the power 0 plus y upon x to the power minus 1, right? Minus log of y by x divided by 1 plus y by x whole square. That is 1 upon x square, and this term is function of y by x. That is, this fxy is homogeneous function of degree minus 2. Then what Euler's theorem says that x del f upon del x plus y, once we know that this function is homogeneous function of degree this, then this is homogeneous, then we can go for Euler's theorem. X del f by del x, y del f by del y is equal to degree of the function, that is minus 2 into function itself 2f, right? Take it this side, add this, right hand side is 0. What we have to prove this, right? The solution of our problem is given here, which we already solved, right? Consider another example. If z is equal to if z is equal to x to the power n function of y by x plus y to the power minus n another function of x by y, then what we have to show that? We have to show that x2 del 2z del x2. Note that del 2 means whatever we are saying, that del 2 means dou 2 by dou z, right? 2xy del 2z del x del y, y2 del 2z del y2 plus x del z by del x, y del z by del y is equal to n square z, right? Then see, z is equal to this. This is given. Now consider this is u and this one is v. If u is this, then u is homogeneous function of degree n. If v is this, then if v is this, then v is homogeneous function of degree minus n, right? Means u is equal to x to the power n function of y by x. It is homogeneous of degree n. Then by Euler's theorem, x del u by del x plus y del u by del y is equal to nu. Similarly, what is v? V is equal to y to the power minus n function of x by y. This is homogeneous. Then x into del v by del x, y into del v by del y is equal to minus n into v, right? See these two equations. These two are the key equations to solving this problem. Right? Now, what we have to do? Again, differentiating equation 1 with respect to x. Right? X del u by del x plus y del u by del y is equal to nu. Now differentiating this, x del 2u upon del x2 plus del u by del x plus y del 2u upon del x del y is equal to n into del u by del x, right? Take this term this side, n minus 1 del u by del x, right? Now multiplying this term by x, then x square del 2u by del x2 xy del 2u upon del x del y is equal to n minus 1 x del u by del x. Right? Similarly, do for v also. Same thing do for the v also. Right? And we obtain using this equation. Right? This is x del v by del x, y del v by del y is equal to this. We already proved one deduction related to this, right? Deduction. Then x del v by del x, y del v by del y is equal to minus b. Using that deduction, x2, right? What is that deduction? That's just remember that. I'm going to tell you. See, what is the deduction? If x is given by this, then x square del 2u by del x2 plus 2xy del u del x del y plus y square del 2u by del y2 is equal to n into n minus 1 u, right? Similarly for b also, x2 del 2u by del x2 2xy del v by del x del y plus y2 del 2v by del y2 is equal to n into n minus 1, sorry, v is homogeneous function of degree minus n, and then minus n minus 1 into v. Using these two equations, right, add this equation 6, add equation 5 and equation 7, right, not 7, sorry, 3 and 5. Adding equation 3 and 5, we got equation 7, and adding equation 2 and 4, we got equation 6, right? Then using 6 and 7, we got the required result, right? Here is the some practice problem. If v is x3 y3 divided by x3 plus y3, then you have to find out this. This is homogeneous for x3 y3. This is equal to x3 1 plus y by x whole to the power 3. Now what you can write here, x to the power 3, x to the power 6, y by x whole to the power 3 divided by x to the power 3, 1 plus y by x whole to the power 3. This is equal to x to the power 3, and this is function of y by x. This is homogeneous function of degree 3. Then apply Euler's theorem and find the first solution. What is this z? Z is homogeneous function of degree 3 by 2, right? Now this u is not homogeneous, but sec u is homogeneous, right? We will discuss this problem in tomorrow class, right? But you guys please solve this problem, and in tomorrow class we will discuss all these three problems. And if you have any other doubt, then note that we will discuss in tomorrow class. Okay, thank you.